I've called this useful radioactive decay equations, and we're also gonna say plus calculations. Okay, right. Let's recap then. We had a look at this last lesson where capital A is the activity of the sample. And what do we say activity? Well, it's the random decay of these radioactive nuclei. Okay, N stands for the nuclei of the sample. Okay, and we talked about, well, the popcorn model. There is no way of determining which of the elements of the popcorn will pop. Same idea with if you got a bunch of nuclei, radioactive nuclei, you can't pinpoint any one of those nuclei, and whether they will emit alpha, beta, or gamma, or whatever. Okay, so we said the activity of the sample is dependent on what we call the decay constant multiplied by the number of nuclei, okay, or potentially radioactive nuclei in the sample. So that's what we learned last lesson, and it links nicely to this second equation here, where you probably have seen, and we can write A equals A naught to the E minus to the power of minus, again, decay constant, and I'm going to use T, which is the time it has taken since the initial activity was recorded. Okay, so we can therefore work out the activity at any particular point in time if we know its original activity and we know its decay constant. Conversely, if we had the original activity and the activity in time, or at a certain time and the time, of course, we could also work out the decay constant, right? You can also write this as count rate, so C. So let me just label these. So this, you could call this activity, or now I'm going to label it as count rate, because obviously count rate and activity are more or less the same thing. When we use a Geiger counter, we are measuring the activity or the count rate. So we can just rewrite it as this. Okay, so we can have C and C naught as well. But you can also have the top term, and I'll just write the top version here where we're just using n's. N is now the number of nuclei. Okay, so we have the original nuclei of the sample, and then what's left over after a certain time interval. So you can see there's a lot of parallelism or symmetry in terms of these equations. All right. However, what I want to talk about in particular is a specific form of when we talk about half-life. So, for example, we all know the definition, or you should know, half-life is the time it takes for half of the radioactive nuclei to decay. So in this case, this is what we refer to mathematically as the half-life. Okay, so half of the original radioactive nuclei have decayed or has been reduced by 2, which means the second half is still the same, but for our time interval, now I'm putting a subscript half to denote, well, it's the time period where this has taken place. Okay, so the original nuclei has halved, or the number of the original nuclei has halved, and I can just say, well, the time it takes for that is the half-life. Okay, now those mathematicians among you will see, well, I've got a common symbol on both sides, so I can actually get rid of the n naughts, can't I? Which means I can then simplify this term here to just simply a half, okay, is equal to e to the minus decay constant times the time interval, or the half-life, like so. Okay. Those among you, you will know that this minus sign means it's a reciprocal function. So basically, I can rewrite this, making it a positive, where I just flip this over. Okay, so I can rewrite this as 2 is equal to e to the decay constant t to the half. Yeah, so we end up with this expression here. Okay. Well, what happens if we log both sides? Okay, we can get rid of the e, can't we? So I get log e to the Okay, that gives me just t to the half, or t subscript half, okay, equals log 2. All right, and this is our next big importance. So I'm just going to put it by itself here. So that simplifies to log 2 equals okay. So I would say this is the next equation I would highlight. Okay, that's going to be very useful for upcoming calculations that we do. Okay, and if you do this on your calculator, log 2 is approximately 0.693. Okay, and this term is going to be you're going to use it quite often. Okay, now especially, for example, if they ask you or they give you the half-life in the question, and they want you to work out the decay constant, well, if you know this equation, all you need to do is log 2 divided by the half-life, and vice versa. If they wanted you to work out the half-life and they've given you the decay constant, you can just do log 2 divided by the decay constant. Okay, so that is useful to make a note of. So make sure you take a screenshot of this, and again, you can always look back at this recording. Okay, so we're now also going to look at what data would look like if we were to do this experiment here. We can see the Geiger-Müller tube there in figure 2 is recording the activity of this radon gas. However, it's not safe to do this at school, so we're just going to have a look at the data that has already been collected for us, that has been conducted safely in labs at universities around the world. Now, if we actually plotted this, it would be an exponential curve, okay? However, you know that if you log an exponential, you'll get a straight line. So what is it telling us here? It says use the table to plot a graph of log C against T. All I'm going to do now is just sketch what it should look like. And your y-axis is obviously going to be log C. Time here in seconds, and you should have, if you plotted it eventually, I mean, you would get a couple of points like that. Without it being a, if it was C and T, it would be something like this, okay? But because we're logging it, we'll get a straight line, okay? And the purpose of getting a straight line is to determine certain factors, okay, or certain parts of our equation, okay? So what I mean by that is, if I rewrite my original equation, C equals C naught e to the decay constant to the t, and I log both sides now, so it becomes log C equals log C naught, okay, plus minus negative lambda t. Okay, Joseph, are you happy with this? What I've done here? Because if I log the e, it basically cancels out. So I'm just left with this top bit here. Okay.
Yes, okay.
You happy with that? Yeah. And I'm also using the log a b is equal to log a plus log b rule there. Okay. That's what I've done there. So basically what we have is log C equals log C naught plus negative decay constant times T. Now, if I now put this in my y equals mx form, I'm going to write it like this, minus decay constant T, this is mx plus log C naught. This is now my C, therefore my log C is my y. This is the form. So do we see? So my y, that's my y-axis. My t is my x-axis. This is my y-intercept. So here I'm going to get a log C naught. And my gradient rise over run is my decay constant. So do you see we have done something quite powerful here, or useful? We've started from the original equation here. Okay, but if we take logs now, what we get is a straight line where we can work out the gradient, and the gradient gives us the decay constant times 24 times 3,600 to give us the time in seconds. And then that's our answer. We get 7.6 times 10 to the 5 becquerels. Okay, so we've answered this. Calculate its activity after 22 days. Question 3 says the isotope of polonium-210 has a half-life of 140 days. A radioactive source has 8 times 10 to the 10 nuclei of this isotope. Calculate the initial activity of the source. Okay, so this is quite similar to the worked example, so you have to make use of the two expressions that we've gone over. Okay, so I've put all that information into this expression we went over earlier. I've converted the 140 days into seconds by timesing 24 and times 3,600. So your K constant should be 5.73 times 10 to the negative 8 per second. And we're going to use the activity equals decay constant times number of nuclei. Yeah, 8 times 10 to the 10 nuclei of the isotope. Okay, and then to get the final activity, we need to multiply decay constant by that 8 times 10 to the 10 number of nuclei, and we should get 4.58 times 10 to the 3 becquerels, or to 2 sig figs, 4.6 times 10 to the 3 becquerels.